No, I see the problem is I loaded a partition software to try and change and resize, but because my hard disk is encrypted, you can't alter it. So spent like 3 hours trying to do that this morning, got nowhere.
You could just get.
I figured a simple solution. I'll put in an SD card.
That's exactly what I was
and I'll set the Dropbox location to be the SD card. And
I was just gonna.
you can choose any file system on an SD card.
Or you could just get a separate drive and connect it. And
But I don't want anything that would fall out. With the SD card, I can actually be pushed in. So I don't know why Dropbox has done that. They're such jerks now.
SD cards are pretty big now. You can get like a 15 gigabyte.
Yeah, but my Dropbox account is only for the school. It's only 2 gigabytes. So I just need any SD card, you know. Come on, guys, what's taking so long?
I'm telling you that when the crowd right now, I feel so down. It takes some more time to like close up. You want to have them?
A beer! Come on! Mabuza! Come on!
You want gum?
Maybe after the coffee. Can we start? Yes. Oh, Mabuza! Don't do that with your eye, please. It'll stick like that. Right. Okay, so we'll continue now. So we have to look at sine and cosine rules, and something you probably have heard about before in middle school, the sine rule and the cosine rule. So we'll start with the sine rule.
Aren't you going to do practical problems?
Yeah, and we use the sine rule and the cosine rule for the practical problems. Okay. Now, the great thing about the sine rule is that it works for any triangle. So last time we saw that sine, cos and tan, we had them for right angle triangles, whereas today the sine rule is going to work for any type of triangle. So let's have a look at the proof here. A, B, B, C, and C. Okay, so what we'll do to get to the proof here, we'll just draw now you should write down the proof, even though it's not on the exam. In semester 2 there's some trigonometry proofs, so it's just good practice to have some proofs in your notebook. We'll draw a perpendicular line here, and we'll call this line height h. And because we've made a right angle triangle, we can say that sine A is h over b. And likewise on this triangle we can say sine B is h over a. We can bring the b up here, we can bring the a up here. So because this is equal to h and this is equal to h, we can say b sine a is equal to a sine b. Or another way of saying it is a over sine a is equal to b over sine b. You can actually continue the logic and say it's equal to c over sine c. This is the sine rule. A rule that you would have seen before. Sometimes you can state it upside down. Sine A over A equals sine B over B equals sine C over C. Okay, got that? Again, I said it a couple of times, but it actually is really important to remember. What's great about this rule is that it works for any triangle, not just right angle. This is really why it's so useful to us. Okay? Okay. So, that's the sine rule. We'll do the cosine rule next, and then we'll have a look at some examples. Okay, can I scroll down? Yep. Right. So back to our triangle, and let's have a look at the cosine rule. I'm not sure why this doesn't fade away. Okay, so again we'll say this is A, B, B, C, C. And again, we'll draw a perpendicular line. Okay. And this time we'll have, we'll call this distance here x. Now if here to here is x, then this distance from here to here, if the total is c, then this distance will be c minus x then. Okay? And we'll call this height here h. So if we look at the triangle here, Pythagoras said that b squared will equal x squared plus h squared. Yeah? And if we look at the triangle here, Pythagoras said a squared, that is loud, a squared equals c minus x squared plus h squared. Okay? Now, what will we do? We'll clean this up a little bit. We'll say b squared minus x squared equals h squared, and here we'll say h squared equals a squared minus c minus x squared. Now, we can make these equal. B squared minus x squared equals a squared minus c minus x squared. So we get b squared minus x squared equals a squared minus c squared plus 2cx minus c squared. I get that right? A squared minus c squared plus 2cx minus, minus x squared at the end. Okay, what's nice is that the x squareds cancel. Okay, so we shall do some rearranging here. I think I'll take this one to the which way around do I want to write this? Yeah, I'll take this one to the left, and I'll take this one to the left, and I'll keep the b squared on the left. So on the left I'll have b squared plus c squared minus 2cx, and on the right I just have the a squared. Okay. Now if I just go back to this triangle, we need to figure out what the x is. We can say cos A equals x over b. So x equals b cos A. So if I go back now, b squared plus c squared minus 2c b cos A equals a squared. Or you could just write that as a squared equals b squared plus c squared minus 2bc cos A. That's the cosine rule. Okay, if you can write this one down, that's the cosine rule.
How's your program going?
Hasn't found any appointments. Been running like, I don't know, 28 hours now. Yeah. Okay, have we got that? Let's see, a couple of people writing. We got that? Have that, yeah? Now, I kind of remember these rules not like this, but more in words. So if you have a look, this is how I remember the sine rule. What the sine rule basically says is, if you have a side and you have an angle that's opposite it, and you have a side, have you an angle that is opposite to it, what the sine rule lets you do is it lets you say side divided by sine of the angle across from it is equal to another side of your choice divided by the sine of the angle opposite to it. So that's kind of how I remember the sine rule. And the cosine rule, I kind of also remember it in words as well. You usually use the cosine rule to find a missing side where you know this and this and you know this angle. So the cosine rule tells us that if you want this side, it's actually a lot like Pythagoras. You can say that side squared equals the other side squared plus the other side squared minus twice the other side by the other side by cos the angle in between them, the two sides. Like it's kind of easier to remember these more visually than as a formula nearly. Let me give you an example of each. So if I said the sine rule, say this is 30, this is x, this is 40, and this is 10, and I want x. What the sine rule lets me do, example, I can take a side and divide it by the sine of its angle on the opposite side, so x over sine 30, and I can say that's equal to, I can take another side and divide it by the angle opposite, its sine, so that's 10 over sine 40, and you realise, oh, now I can easily get the x. All I have to do is take that out from there and bring it up there and then put that in on the calculator and I'm finished. So can you just type that in and we'll see what we get. 7.8? Is that right? Yeah?
7.7. Yeah.
Okay. Okay, can I scroll down? Not yet? Can I scroll? I see people writing. Sahra, you have this? Yeah. We'll have a look at cosine rule now, okay? So, cosine rule. We'll say x, 5, 6, 40. Okay. So, with the cosine rule, is a lot like Pythagoras. You say x squared equals 5 squared plus 6 squared. But then the extra part is minus twice 5 by 6 by cos 40. That's the extra part. So, if we just type this in, 25, 36, 60, cos 40, we can get the x here. It's our second example.
Answer is 3.8.
3.8?
Yeah, 3.8.
Mm-hmm. We got that?
Did you get the same answer?
Yeah.
Now, we will have a look at some practical problems. Okay. So in the exam, I'd say 50% of the time they just give you a triangle and they ask you to find something. And then 50% of the time they give you a little practical problem, like a little story problem. So let's have a look at some practical ones, because they're the tricky ones. Right, we'll... say, I don't know, some building here. Okay, so in this one, we imagine we have a student, and they mark a point off the ground, and they look straight up to the top of the building here, and they measure the angle of elevation, which is actually quite easy to do. So let's pick a number. Let's just say that angle came in at, we'll just say 40 degrees. And then what's also quite easy to do is to walk a certain distance forward. You know, if you have a measuring tape or a meter stick, you can measure a distance. We'll say 2 meters in this case. Okay? And then the student measures the angle of sight to the top of the building again. And of course this angle will be bigger because they're now closer to the building. And they measure that angle, let's say 50. Not really to scale. Now, there's only 3 pieces of information here, but that's actually enough to work out the height of this building here. Okay? Now, I will do this, but it's good for you if you can try it first. And I'll give you a little hint. My hint is to first find x, and I'll call this here x. Well, yeah, maybe not first, but it's useful to find the x. The first thing you should do is write in all the angles. Okay, I'll give you a minute to try that. I think some of you will get this. Let's have a look here. If you're still working, that's fine. Let's have a look now, okay? So, we should fill in all the angles. Because this angle is 50, it means this one here has to be 130. And 40 and 130 make 170, so this one up here must be 10. And that's 50 and that's 90, so this one has to be 40 here. Okay, so we have all the angles. Now, should I use the sine or the cos rule to get the x? And the hint is, I should imagine this triangle here. Sine rule will work. I could say x over sine 40 equals 2 over sine 10. Yeah? So x is 2 sine 40 over sine 10. Okay, fine. Does someone have that, please? What's that? 7.4. Okay, we'll do 403. Now, lastly, I want to get the h here, and I know the x. So what would be the best way to get that? And remember, it's a right angle triangle. Yeah, you could say sine of 50 equals h over x. Yeah? So h equals x sine 50. So your previous answer times sine 50. So what do you get here?
5.671.
5.671 then. Yeah. Where the sine 10. Yeah. Can you see this 10 here? Is it too small? So what I'm doing is I'm saying x over sine 40 equals 2 over sine 10. I'm using the sine rule like that. Yeah.
Can you explain how you use the sine rule for
I'm not actually, I'm just using the regular sine equals opposite over hypotenuse because it's a right angle triangle. Yeah.
Also, so like the right angle triangle,
Yeah.
if you think about it, because sine 90 is 1.
Yeah, so you could use the sine rule like that, yeah. Because the sine rule turns into the regular sine rule in cases of 90. And what does the cosine rule become in cases of 90? Yeah, what rule? It becomes Pythagoras. Because cos 90 is 0. If you think about the formula, a squared equals b squared plus c squared. If the cos 90 is 0, then it becomes Pythagoras. So you can think about as the cosine rule is like a version above Pythagoras, and the sine rule is a version above sine. Okay, another example now. Can I scroll down? Yeah. Can I just borrow the calculator because I want to make up some numbers here.
I'll go to first.
Okay. Right. I'll just give you some info. Okay, so he has a rope. That's a rope. She has a rope. Okay, how much rope do they have? Let me think. 2 ropes, correct? Yes. Yes. Maybe I won't tell you. Maybe that's what I'll ask you. Okay, so and there's a balloon here. There we go. Look, I'm making it exciting. Okay, so both of them use their rope to keep the balloon from flying away. And each of their ropes makes an angle with the ground, of course. So, you can imagine the balloons floating up here, and they have their rope. Each of them is holding the balloon in place with their rope. So I need to give you, what will I give you? I'll give you the angles. Let me give you the angles. So his rope makes an angle of 53.13 degrees to the ground. And we'll say hers makes her one is a 67.38 degrees to the ground. How much more information do I need to give you? Every angle. I don't want to give you too much information.
I think it was one side. One side. Yeah. One side.
Yeah, but whose will I give you? Maybe I'll tell you how high up the balloon is. Yeah. So the balloon's height from the ground is 12 meters. Yes, that will do. Okay, so I want to know how far apart they are.
You want to know the base?
Yeah, the base. And they're obviously standing on ground, if anybody's confused. Yeah. Question? So my question is, how far apart are the two of them?
That's perpendicular?
Yeah. Well, which part? Mubarak! Are you working on this? Okay, fine.
Yeah, the height of the balloon.
Are you working on this? Yeah. Okay, well then do so quietly, please. I can't hear his question.
The height of the balloon.
Yes. Well, the straight line here is perpendicular.
Yeah.
Okay. Got an answer? What's your answer?
14.
I think that is right. 14 meters, yeah. There's two answers though. That's two answers. You only gave me one of the answers. So let's have a look. Well, I'll just draw it, but I won't say anything. So what was this angle here?
53.50.
And this one?
67.3.
Okay, and the height here you know is
12.
12. Okay, so I mean you don't actually need any particular special rule here. You could just use sine cos tan because it's 90 if you wanted to, couldn't you?
Yep.
Because you could call this x and this y. Yeah. So you could say sine 53.13 equals 12 of... Oh, sorry, not sine. What should I use? Tan. Tan 53.13 equals 12 over x. And tan 67.38, what will that equal? 12 over y. So you can say x is 12 over tan 53.13 and y is 12 over tan 67.38. This is 9 and this is 5. So the total distance between them is 14. But what was interesting about this one, which is why I wanted to do it, is there's actually a second answer. See, they could actually be closer together, but all the information still remained the same. Now, I want you just to take a minute to see, can you draw this triangle again with the same angles and the same height of 12, but have the two of them closer than 14 meters? Just take a minute and see if you can draw it. And if you figure it out, tell me how close they are then. And they're not underground or anything like that. Question? Yeah?
Is it okay to use I use the Sine Rule?
Oh, absolutely. Yeah, absolutely.
Then I got 4.67.
Did you round off too early? We should be able to use this Sine Rule. You use the Sine Rule?
Yeah.
And you got the same answer?
Yeah.
Right, did anybody figure out their possibly closer distance? No? No? Okay, I'll show you. So there are three, just to be clear, there are three pieces of information that you're given. The boy's angle, the girl's angle, and the height of the balloon. Is there any way I could draw this so that they're closer together but still keep the angle and height the same? So what you could have done, you could have had the boy here as before with the, the girl here with the 67-degree angle, and then you could have just had the and then the boy here with the 53-degree angle here, and this is 12. Yeah. So the distance here between them would now be, I think, 4 meters if you work it out. Yeah. Now the reason I did this is because to show you sometimes with these trigonometry problems you actually have two ways to draw it, sometimes two ways to think about it, and like you said, it depends on if the angles are all acute or obtuse or things like this. Let's see. Yeah, I don't think there's anything else to say about that. Okay, nobody saw that one? No? Okay. You want to recalculate? I think it's 4.
Can you do 5?
Huh?
5?
What's 5? Oh, could you change the distance? I think it's only these two. I think so. Because if I was to make them closer, their angles would change. Okay, we'll do another one now. Can I scroll down? No. Not yet? Okay. That one? 33. Does anyone have a protractor, for measuring angles? No? Somebody must have one. Come on.
Keep back at home.
Let's do it at home. No. Nobody has a protractor. Are you kidding me? For measuring angles. The half circle. Oh, good. Okay. If I can borrow that, please. Yeah. Right, and now I need some string. Anybody have a piece of string?
Use the ruler. Can't you just choose a ruler?
You have a piece of string? Good. Where did that come from? All right. Thank you. Right, now I need a bit of sellotape, so...
Okay.
Okay, I'll grab it.
I know somebody might have sellotape in their pencil case. Oh, wonderful. I need a little piece.
Really?
You can start with yourself. You're fresh from all the sellotape as well. Goodness. Yeah, yeah. Steady. That's enough. This is fresh sellotape now. It would work even better. Oh, wonderful. I just need like a little piece to stick this onto it. These are all hard. Right. Got your scissors there. That's what I'm going to go. And then just rub it on. There we go. Right, and lastly, just like a little rubber or eraser, just something to tie at the end here. Yeah, okay. You saw the bit of that sellotape? Right, so I'll give you an example now. Hey, listen up. I have to construct this now. We're going to figure out how high up the room is. Alright, so. No, Right. Now, you can help. So I'm going to look at the top of the room and I want you to tell me what angle measures out here. You understand? So I got an angle. Right, what angle is that now? Is it still shaking? Just guess from where it's dangling around. Yeah, but it's 10, 20.
Oh,
Yeah.
this way or this way?
Towards me. So like this is 0,
Oh,
10, 20. So it's about 20 something, is it?
Yeah, it's about 23, 24.
Alright, write that down. 23 degrees for the first angle.
Is this the thing that they use to measure the angle of the sun?
Yeah, but obviously my one is not as advanced as that one. Right, so and then we'll move 1 meter forward and measure another angle. Right, so let's see now. Okay. Right, what's that now?
It's about 26, 27.
Right, 27 degrees now. You got those two? Yeah? And the distance is a meter. 27. Right. Calculate the height of the room, please. Now, that's all, yeah. Now, this is made start with car. So that's somebody's rubber, somebody's scarf. Well, that's your photographer with your sellotape. So I'll let you disassemble it then, okay?
What's the
A meter. It's the distance between them.
find the height?
Yeah. It's just like the example I did of the tower. Were you able to disassemble it? Yeah, okay. Huh? One meter. Yeah. Sorry, is this your height, sir? Maybe the height of the actually can't find somebody. Do you want to push it inside?
It's like
You're ready, sir. What, sorry?
Oh, thank you so much. I'm gonna tire right back.
I think the angle is the other way around. 22 is the first one.
Yeah, but this one's bigger.
No, you have it backwards, the other way around. What you got? Too much error. Right. You got an answer? It's just like the example of the tower one I gave you. Yeah. Code C.
You want this side, right?
Yeah, correct, yeah. I'm hearing two different answers here. Some people are saying 2, some people are saying 5. What did you get? What did you get? That's what someone else got, yeah. Huh? Yeah.
Just gave one. Like, you didn't write it, you said it.
You have the triangle drawn the wrong way. It's like how I did the tower picture. Yeah. What did you get? 2.5. 2.5? Okay. So, obviously, Mubarak did a bad job of measuring the angles from my advanced device. It's okay, Mubarak. It's okay. Yeah. I know.
You're getting like
yeah, I think a lot of people are at 2.5, to be honest. Which is obviously wrong, but you know, I have to work with who I have to work with, and I can't change that. So. Now, anyway, obviously, if you had it properly made, these actually, does anyone know the name of what I used to measure the angle?
It starts with S.
No, it doesn't actually. It starts with C.
Oh, it ends with N.
Don't think so.
No?
Now, does anybody know what this is called? No? For measuring the angle? So anyways, the device that you use for measuring the angle of elevation is called a clinometer. Yeah. I don't think so. Oh, well, the one that's used on ships, is it?
Yeah.
It's called a sextant.
Yes.
But that's this for measuring like the angle for the height of buildings is clinometer.
Okay.
Yeah. Now, the reason I did that, Mubarak, listen. So I wanted demonstrate in principle that you could actually do things like measure the height of mountains if you had a device accurate enough to measure the angle, which you can imagine is not it's not too difficult. You can if you make a proper one with a actual viewfinder tube on it that you can actually with a little sort of like a little telescope, you could pinpoint the top of the mountain. So what's useful about this is if you can measure the height of a mountain, then you can do something like measuring how big the Earth is, which is actually question 5 here. So I want to do number 5 with you, but I want you to try it first. Before you do number 5, I just want you to understand that this actually was how people first estimated how big the Earth was. First they measured how big a mountain was by using a method that I just showed you, and then climbed to the top of the mountain and then looked to the horizon and measure the angle to the horizon. So if you read the story in number 5, I'll give you a couple of minutes to try it, and then we'll see if you can get it. Number 5, just give that a go. You have the picture there to help you. So in the picture I'm looking for or.
For R?
The radius of the Earth, yeah. In number 5, isn't it? Or do I have the wrong number? There's yeah.
But there's 2 R's.
Yeah, they're both the same.
Yeah.
Because it's a circle.
Yeah.
Mm-hmm. Right, let's have a look at this together. So just to help you picture what's happening here. Yeah, you have it? It's not that long to do when you see it now. So just to help you picture what's happening here. When you get to the top of the mountain, you look to the horizon, and what you do is you measure the angle downwards. Okay, so obviously you can imagine if you're looking down to the horizon, if you're on the top of a mountain, you know, there'll be a small angle downward here. You can use the climometer to measure this angle as well, okay? So in this particular story, you know the height of the mountain. What did I say it was? 321 meters, isn't it? So you know that this height here is 321. This is the radius of the Earth, which you don't know. And this is the radius of the Earth, which you don't know. And when you look off the horizon, what you're doing is you're making a tangent with the circle of the Earth. When you look at the horizon, your line of sight is a tangent to the surface of the Earth. So can you see that? That there basically is a 90. Yeah? Now, yeah?
Isn't the line to the right, isn't it, yeah, this one, isn't it R plus 3?
It is, yeah, those two added together, yeah. So, if you know this angle, can you know this angle? Yeah, what is it?
Minus
90
90.
minus alpha. And if you know this angle, can you know this angle?
Yeah.
Yeah. It will be, what would this one be? It will be 90 minus the other angle you just got. And that actually works out to be alpha. Now, if you look at this triangle and this angle here, if you're talking about this side and this side, do you need sine, cos, or tan? This side and this side.
Cosine.
Cos, yeah. So you can say cos alpha equals what? What's the adjacent for this angle?
R.
Yeah. And the hypotenuse?
R.
No.
R plus 3 to 1.
R plus 3, 2, 1 then. Now, I tell you what the alpha is in the question. What did I say it was? 0.567. That's equal to R over R plus 3, 2, 1. I want you to solve for R. Tell me the R here. Oh, and my advice is try to wait until the end to use the calculator, okay? Just to be more accurate, if you can rearrange terms and wait until the end.
Thank you.
I asked for two significant figures. Question? Did you? I didn't type this in on the calculator, so. Oh, okay, sorry, I'll fix that. What did you get? You typed in exactly this?
Yeah.
Okay, what you get?
6.5.
Yeah.
5.
Okay, so it's 6.6 if I do.
6.500.
Okay, 6.500. 000. So 6.500 kilometers. Yeah.
So I think it's better to write 6600.
Yeah, that's what we're going to run it up with.
Yeah.
5.
Oh, is it? Okay, so 6.6 then. Okay. Yeah, okay. The reason why I think this is so interesting, because if you ultimately think about it, your clinometer with your meter stick, these two devices is enough to measure how big the Earth is. Which, you know, is fairly impressive with a meter stick and a protractor with a rubber hanging out. But, you know, like, it's impressive enough. You just need to find a nearby tall mountain to climb. You could work out the radius of the Earth. And this is what people did maybe about, I don't know, about 1,000 years ago perhaps.
And this is accurate?
His estimate, the person in the story, was pretty accurate. There was only like a 1% or a 2% error. So it's not bad for 1,000 years ago, you know. Does anybody know the person I'm talking about in this question 5? Is this a name that anyone recognizes?
Albert.
Yes? Do you know him or not? No? No? Arab students do not recognize this guy? Is he not like the Arab version of Newton, or?
Isn't that like the guy that made trigonometry? He's like the Arabic version of Newton.
He would have done a lot on trigonometry, yeah. You know?
I think so. I know the guy that did trigonometry is like the Arabic Newton.
He might have done some stuff on algebra. I don't know. You don't recognize his name?
He's an Iranian scholar and polymath.
Yeah, no, but did you know him before you saw this name? No, okay, so he's not.
Arab, he's Persian.
He's not. Oh, he's Persian, is he? Oh, well, that explains it. So.
It does.
Yeah. Okay, so if you can. If you can try these questions now. I don't usually do, or what I need to say
How
is,
are you getting that?
hmm?
Use it.
Well, that's what he taught me. Oh,
No.
it's the question says 2 significant figures.
I'm not getting the same answer, but
I'm getting the same answer.
Huh?
I might be
No.
doing something.
Yeah, he's right.
Yeah.
That's right. You're wrong.
Ah, don't be so harsh. Deliver it gently. Okay, listen. So I don't want to do, or rather I need to say, this lesson, because it's quite tricky, I don't usually do it in 1 hour. I usually give students time to try these, okay? So we won't do a second topic. I want to use the remainder of the time for you to try figuring these out. They do come up in the exam. They're usually a section B question in the exam, which makes it worth 15%. Okay? Now the good news is, in the exam they usually give you a picture as well. It helps a little bit, you don't have to draw it. Okay? So can you do your best, see how many you can get done. If you don't know how to do one, skip it and come back to it, okay? Don't spend too long trying to figure it out. Because sometimes students get a bit stuck on the first one. They find the number 3 is like what we did in class, as is number 4. If you wanted to try, we could start with those even.
it literally gives you math algebra.
Hey! Stop.
It should give you 65555.
You missed the bracket.
So we're doing all of them?
Yep, all of them, please.
Oh, that's nice.
Right on. Looks good. Looks good. So you got this, good. So you're saying, where's get the half one now, I wonder? That's the half, isn't it? Okay, what should I look at here? Uh-oh.
اسمعني هو ياسر جاني بالعربي
Can I please see what is that? Show me. It's meant to look. It's meant to be red. It's meant to be an Arabic language.
It's supposed to be in English, yeah?
It's meant to be in Arabic and English. It's meant to be red. Red-ish. It's a red paper.
Yep.
Tell them to send the picture.
42 is a straight line. Yeah. That's right.
My friend was also complaining about the equivalency calculus when I went back to Dubai. He's like, dude, you changed